Hello friends, welcome to this video on power spectral density. This video will introduce you to the definition of power spectral density, how it is related to the autocorrelation function, and then the properties of power spectral density. We will also be trying to define what is meant by cross power spectral density and define its properties in this video. Come on, let's move on into the video. Let x of t be a stationary process. That x of t can either be a triple-S process, that is strict sense stationary process, or it can be a WSS, namely wide sense stationary process. And let this have an autocorrelation function which is given as Rxx of tau. Then we take the Fourier transform of this autocorrelation function Rxx of tau, and this Fourier transform is called as the power spectral density or power density spectrum of the random process x of t, and it is denoted by the script Sxx of omega, x standing for the random process from which we have taken the element. So we define Sxx of omega to be the Fourier of Rxx of tau. Now, how to define the formula for a Fourier? Fourier is nothing but integral from minus infinity to infinity. Whatever be the input you have, give this as input, multiply it with e to the power of minus I omega tau, and if you have tau over here, you integrate with respect to d tau. The idea or the way in which we can remember this is, if you have Fourier f which is positive, then exponential sign over here will be negative in nature. This exponential which is negative is a function of both the parameters omega, which is the input for your power spectral density, as well as tau, which is the input for your autocorrelation function. So this is an exponential function of e power minus I times. It is a function of both your omega as well as tau. But the integration will be carried out only with respect to the input value. Which is the input value? Input value is going to be in terms of tau. So we integrate it with respect to the variable tau. So our Sxx of omega, which is the Fourier, is of the autocorrelation function, is defined as minus infinity to infinity Rxx of tau e power minus I omega tau d tau. Now, whenever there is going to be a Fourier defined, we can also define the inverse Fourier. So what will this inverse Fourier give us? So what we have is Sxx of omega, which is known to us, and then this can lead us to find the autocorrelation function Rxx of tau by using the inverse value. Okay, what did we write? We wrote Sxx of omega to be Fourier of your autocorrelation function Rxx of tau. So if I want this Rxx of tau, inverse operate this Fourier on opposite side. So what will happen? This Rxx of tau part will now be equal to f when it goes to the opposite side, or it is going to be, it is inverse operation of, it's not actually going to the opposite side. What you do is operated by an inverse operator. So Fourier inverse operator of Sxx of omega. So how to define the inverse Fourier? Inverse Fourier has an 1 by 2 pi, the constant part in front. The integration is still the same from minus infinity to infinity. Take your input Sxx of omega and note down that you have an exponential function of e power I omega tau, and what is the input function over here? With this omega. So integrate it with respect to omega. So there is also a shortcut to remember over here. When you have inverse minus sign over here, your exponential takes a positive sign. Now compare, when you have a positive sign over here, your e will have a negative sign. But when you have a negative sign for your Fourier, your e will take a positive sign. So in this way we can remember this formula And you also have to keep in mind, whenever it comes to autocorrelation function, there will be a constant 1 by 2 pi which is to be added to in the front, or like multiplied to in the front. Now we call this Sx of omega and Rx of tau. They form a Fourier transform pair. So they happen or occur as a pair of data. Okay, so whenever we transform a autocorrelation function to a power spectral density to an autocorrelation function, then it can also revert back from the autocorrelation. I can get the power spectral density. When you take the Fourier, you can take the inverse Fourier. So this happens or always occurs as a pair. Now coming to the next quantity, this relationship or the definition which we are given, Sx of omega, which is the Fourier of the autocorrelation function, is also sometimes referred by the name Wiener-Kinchain relationship. Wiener-Kinchain relationship. This Sx of omega, what does it actually represent? It gives the distribution of power or energy of the random process x of t, and it gives it as a function of the frequency value. What is frequency? Our omega is our frequency. So since it gives us how the power is distributed or how the energy is distributed, it gets the name power spectral density function. So what does this Sx of omega represent? It represents the distribution of power or distribution of energy. And in terms of which function we denote it as? We denote it as a function of the frequency. Now moving on to the property. What happens to our Sx of 0? What we know about our Sx of omega? Sx of omega is integral from minus infinity to infinity Rxx of tau. We have e power minus I omega tau. Since tau is here, we have it as d tau. Now what do? I put omega to be equal to 0. When I replace this omega as 0, what happens to the omega over here? This omega gets replaced as 0, and we know that e to the power of 0 turns out as 1. So this becomes Rxx of tau product 1 times d tau. And what does this represent? The value of the spectral density function at 0 frequency, which means omega equal to 0. What does this represent? It represents the total area under the graph of autocorrelation function. Normally we say that minus infinity to infinity f of x dx. So when we measure from over here to here in normal distribution also, minus infinity to infinity, the probability function, what does it measure? It measures the total area under the graph of your f of x. So what is the graph over here? The graph over here is Rxx of tau. What is Rxx of tau? The autocorrelation function. So it measures the total area under the graph of autocorrelation function. The second property is that the mean square value. How do we denote the mean square value? By expected value of x square of t. And this expected value of x square of t is nothing but our Rxx of 0. This we have seen in the properties of autocorrelation function. Okay, so whenever we have the function Rxx of tau, you have it as expected value of x of t into x of t plus tau. So when this tau happens to be equal to 0, what will happen? This will become 0. So this becomes x of t into x of t. Hence you have it as expected value of x square of t. So what is expected value of x square of t? It is nothing but Rxx of 0. What does this Rxx of 0 represent? In a similar way, in your inverse Fourier, 1 by 2 pi, when this exponential part with a positive I omega tau is made it as 0, omega becomes 0, tau becomes 0 over here. So e power 0 will become equal to 1, and I have it as Sxx of omega d omega. And what does this represent? This represents the total area under the graph of, what is the graph over here? The graph of spectral density. So expected value of the x square of t, which is the mean square value, is nothing but the total area under the graph of spectral density. And property number 3 says, for a real random process x of t, this function, the power spectral density function, is going to be an even function of omega. What does that mean? Even function of omega means whenever I replace this omega with minus omega, I get it to be the same as Sxx of omega. So when I replace omega with minus omega, what happens? I get it to be the same function of omega. The same property holds true for an autocorrelation function also. Autocorrelation function is also an even function, but it is a function of tau. Over here, this is a function of omega. And fourth property says Sxx of omega is greater than or equal to 0 for all the values of omega, which means this power spectral density is going to be always going to be a positive value for you. Greater than or equal to 0 means it always remains positive for all the values of omega. So these are going to be few properties of the power spectral density. Next we move on to define what is the average power in a process. So there is going to be a spread of your energy or distribution of your energy. So whenever there is going to be the distribution of your energy, we need to know what is going to be the average energy that can be transferred or the average power that can be transferred. So how to get this average power? This average power, which we denote it as Pxs, is defined as 1 by 2 pi integral from minus infinity to infinity Sxx of omega d omega. But we notice that this Sxx of omega is nothing but Rxx of 0, which can also be defined as expected value of x square of t, which we call it by the name mean square value. Okay, so the value or the mean square value or the average power in a process is going to be all the same. And so whenever they ask us to estimate the average power in a process, we can just estimate it by substituting tau to be equal to 0. Now comes the Wiener-Kinchain relationship or the theorem. First we saw the relationship. This is the theorem. Let x of t be a real WSS process which has a power spectral density Sxx of omega. Let xt of t be the position of the process x of t in the time interval from minus t to t. That is, xt of t, when t varies between minus t to t, it takes the value capital X of t. Now capital xt of omega is defined as the Fourier transform of your xt of t. Then what does this xt of omega give us? So the power spectral density can be defined in terms of limit t tending to infinity 1 by 2t expected value of modulus of xt of omega the whole square. This theorem is referred as the Wiener-Kinchain theorem. Okay, next we move on to cross power spectral density. So whenever we have two quantities to be the same, you refer it by the name auto or without the word auto. When one of them is going to be x and the other one is going to be y, then you refer it with the name cross. So you call it as cross correlation, or now over here, since it is going to be power spectral density, you call it as cross power spectral density. So how do you denote it as S x y of omega denotes the cross power spectral density of x of t and y of t, where this x of t and y of t are going to be two jointly stationary process which is going to have an autocorrelation, not autocorrelation, cross correlation over here. So r x y of tau. Now this S x y of omega is minus infinity to infinity. The same formula what we have used, the Fourier formula. When it is xy as input, it is xy as input over here. When it is xy as input, when it is xy of input over here. So the only change that happens is when it is xy here, give xy as input. When it is xy as input, give over. But if it changes to yx, so change over here also as yx. So yes, yx of omega. So you have two types of cross power, one with respect to x and y, the other one with respect to y and then x. So for this you will have to give cross correlation r x y. For this you will have to give the cross correlation r y x. So just replace it with the formula, you will get your answer to be done. Now moving on to the last slide where we see about the properties of this cross power spectral density. This cross power spectral density, when you replace this omega with minus omega, this xy gets replaced as yx. So xy of minus omega is, it flips this xy as yx and this minus sign gets flipped as omega. Okay, so it is neither an even function, neither an odd function. So what is the only property? When you have it to be minus sign, it flips the random variables from xy to yx, and then it flips the frequency from negative to positive. The second property says that the real part of sxy of omega and real part of syx of omega are going to be even functions of omega. So now you can say that they are going to be real part of sxy of omega is going to be an even function. So even function means what happens? Real part of xy of this omega, if I replace it with minus omega, it still remains to be the same. Similarly, if it is going to be xy replaced with yx, it is also again going to be the same. Next property says imaginary part of this sxy of omega and imaginary part of syx of omega or odd functions of omega. What do you mean by odd function? This imaginary part of sxy of omega will be equal to the imaginary part of sxy of minus omega. So if my f of x is equal to f of minus x, you call it as even function, and this f of minus x is going to be equal to minus sign of f of x. Then what do you call it as? You call it to be an odd function of omega. So this is going to be imaginary part. If it is going to be what will happen? This omega, if it is replaced with minus omega, what will happen over here? If this omega is replaced with a minus omega, what will happen? A minus sign gets outside of this. This becomes minus sxy of omega. And why do we get this real and imaginary part? Whenever we have a complex number which is of the format a plus ib, this is called as the real part and this is called as the imaginary part. Okay, so this real part will often power spectral density. This part will remain as an even function, and this part, which is b, the imaginary part, will always remain to be an odd function. We give this as a complex number because we have this e power minus I omega tau. So this can be this is involving an I. So what it generates is going to be an complex number. Okay, so you need to have in mind this power spectral density is going to be related with a complex number. The next property states that if x of t and y of t are going to be orthogonal to one another, then what happens to the cross power spectral density? They vanish. Sxy also vanishes, syx also vanishes. So what we have is, if x of t and y of t are orthogonal, then sxy of omega is going to be equal to 0, syx is also going to be equal to 0. The last property states that if x of t and y of t are going to be uncorrelated, what will happen if they are going to be uncorrelated? Then sxy of omega. So now uncorrelated means there is no relationship. So e of xy can be written as e of x product. This is going to be e of y. So you can separate e of x and e of y separately. But what happens? It gets multiplied by 2 pi times del of omega. What is this delta of omega? This delta of omega is nothing but our Dirac delta function, which is defined as minus infinity to infinity e power minus I omega tau d tau. Okay, so what we have is, if orthogonal, the cross power spectral density vanish. If they are uncorrelated, they become written as product of the random processes means, but you'll have to multiply it with an Dirac delta function. So these are going to be few properties of our cross power spectral density.